Aujourd'hui, nous avons l'honneur de recevoir le professeur Janosh ORTMANN, qui nous vient de l'ESG à l'UQAM et qui travaille donc il s'intéresse à tout ce qui est intelligence artificielle et surtout l'optimisation de la prise de décision. Donc, le professeur Janosh a reçu déjà son PhD ou doctorat de l'université Warwick et il a complété des post-docs dans pas mal d'universités, dont l'université de Toronto, l'université de Montréal et Concordia. Donc, il s'intéresse à la prise de décision, à l'analyse de la prise de décision et aux algorithmes d'apprentissage machine dans le non supervisé et l'apprentissage par renforcement. Aussi, Janosh est affilié à plusieurs groupes de recherche et d'études, dont le GERAD, un grand groupe bien connu affilié au HEC, et le CRM ou le Centre de recherche mathématique. Donc, le titre de la présentation de Janosh aujourd'hui est Machine Learning for Stochastic Optimization. Voilà, merci. Je laisse Janosh commencer sa présentation et je le remercie aussi beaucoup pour avoir accepté à présenter aujourd'hui au séminaire DIC.
So first of all, thank you very much for this invitation. I'm really happy to have this opportunity to talk a little bit about my work. It's particularly a pleasure to be sort of locally here at UQAM. It's not that often that I speak here, so I'm very happy about that. So what I want to talk about today is some applications of machine learning, specifically mostly unsupervised machine learning in stochastic optimization. So what that requires me to do is to talk a little bit about stochastic optimization and kind of give you a rundown of that, because I don't know, it's probably not the main interest for most of you, but nevertheless, I think there's some interesting things that can come out of it if you combine ideas of optimization with machine learning. So this is a bit different to maybe a lot of talks. So I see a lot of talks where people use optimization techniques to help along some machine learning algorithm or something like that. My interest is kind of the other way around. So I want to solve different optimization problems using machine learning, or help solve problems, better understand optimization problems using some form of machine learning. So in general, the sort of meta problem that I'm interested in are problems or decisions being taken under uncertainty. So there's some sort of obvious examples. For example, when you plan a new metro route, a new subway route, you don't really know in advance the number of passengers that will take this route. If you're planning a warehouse, okay, you have some idea, obviously, what goods you might be passing through this warehouse, but not necessarily in a way that that is clear. And infrastructure is a sort of obvious example where a lot of investment has to come up front, and it's not necessarily clear. It's not necessarily clear in advance how these things pay out. Will people actually use this new system? So in Quebec, we have this discussion right now: should we build a tramway? Should we build a car tunnel? And part of the problem in the discussions is that people don't actually know how many people will use it. I mean, there's other issues as well, but that's one of them. So that's what I want to investigate a little bit. And so on the mathematical side, so this is kind of the problem on the mathematical side. What you want to do is you want to minimize some function. You can maximize it as well, but that doesn't really make any difference, subject to some uncertain parameters. So the sort of mathematical formulation is this: that I have a set of decisions y that I can take, and then the payout. Let's say, so in optimization we mostly think in cost, but you can sort of put a minus sign in front of it, and then you optimize you want to maximize some quantity. Then you can sort of say, well, okay, I want to minimize this cost subject to some set of uncertain parameters. So that's before we do any maths, there's a modeling question. How do we interpret this even? Because if if these parameters are uncertain, it's not clear what does it mean. So sort of one of the classical approaches is to simply take some point estimate. So take some specific non-random estimate of your uncertain parameters, and then just replace the optimal function by this. And then you just optimize with regards to this. So for example, an obvious thing to do would be, if you're thinking probabilistically, would be to take the expectation of the parameters. Or it could be the most likely outcome. There's different ways that decision makers take this approach. The problem with that is that it sort of hides a lot of the structure. So there are lots of examples. Think about, for example, the classical news vendor problem, where you want to offer different newspapers, and you don't know exactly how many of each type of newspaper is being demand for. Well, if you just take the most likely outcome, well, then one of the newspapers will have the highest demand, and then you will just buy that newspaper. So the deterministic solution doesn't allow you to hedge for anything. You're just going to buy one set of newspapers and sell it to your clients, and all the customers that come that don't want to buy this one newspaper will be turned away. And this is kind of typical, that the solution that you take, that you do when you try to look for when you take into account uncertainty, is hidden if you take any particular outcome. And it doesn't matter which one of the outcomes it is. In this case, it's not the problem that I chose the most likely demand distribution, but for any demand distribution, one of the newspapers will be more advantageous. So I just provide this one newspaper. So in general, that's not a very good approach. Instead, what people do is we can go in the sort of robust optimization direction. We can say, well, we'll look over all the possible parameters. We'll take the worst case. Okay, so we want to minimize some cost function. We just look over the entire parameter space. We say, well, what's the worst case? What's the worst that can happen? Okay, that is something that can be done, and that has been done successfully. The downside to it is that you are, on the one hand, quite pessimistic because you're looking at the worst case, but it's also really sort of sensitive to what you think the worst case is. If there's an even worse case, you haven't even considered that. So that sort of relies heavily on you having a really good understanding of what the set of parameters can be. But on the other hand, it might be that the worst outcome that you're actually optimizing for isn't actually all that likely. So you're optimizing for a case that might not happen or might not happen very often. That's bad as well. So one way of dealing with that is to think a little bit more probabilistically. And I'm not saying that's better, but that's definitely better for me because I like probability. I like thinking about sort of modeling uncertainty. So what the direction that I would go in if I was looking at such a problem would be to take some sort of stochastic approach. There's a little typo in the slide. I can just see the D shouldn't be there. So I'm just basically, instead of looking at minimizing the function G, I'm going to minimize the expectation of that function. So that requires for me to think about, what does that even mean? What is the expectation? Well, the expectation is with respect to these uncertain parameters. So that obviously forces me to somehow give some probabilistic interpretation of the parameters. So one thing I could do is to just say, well, these are random variables. And then what I can do is simply say, well, I'm taking the expectation over these random variables. So that requires me to say, to go to the decision maker, to whoever's modeling the problem, and ask, well, what is the probability distribution for each one of these uncertain parameters? I can do that. It's not usually the case if in most sort of decision-making situations that someone's going to give me some complicated multidimensional distribution of these parameters. But that in principle, at least, can be done. So the downside, of course, of doing this, maybe sort of obvious, is that this requires me to be able to calculate this expectation. I have to actually work out what the expectation is if I want to minimize this function. In general, that can be quite complicated and can be quite difficult. So I have kind of two problems. On the one hand, I have the problem that I need to understand quite well what is the distribution of the Xi. And on the other hand, I need to be able to somehow analytically work out what's going on, working out this expectation. So one sort of compromise in this direction is, instead of thinking about some abstract probability distribution, is to think concretely about certain outcomes. And this is actually sort of in a decision-making context, something that people often do. They think about scenarios. They think about different outcomes that could happen. So for example, I could sort of say, well, you know, if I'm thinking about the transport planning thing, well, let's say I want to build a new tube line in London. Okay, I want to build a new underground line. Well, then different things could happen, right? So for example, I could have what's happened in London in the last few years. I could have quite a heavy growth, or that's at least what happened until 2016, 2017. And then another sort of quite unlikely scenario happened, which was Brexit, which sort of had a heavy impact on the city of London, on different aspects of economic life in the UK. And therefore suddenly maybe led to less transport. And another obvious example would be a pandemic, which has massively depressed the demand for transport, public transport in general. Similarly, for a warehouse, you can think about different sort of, you know, let's say a new campaign Sometimes people talk about high, medium, or low demand. So, in the best case, this will happen. In the medium case, this will happen. And in the worst case, this will happen. So you kind of build different discrete scenarios for each one of your uncertain parameters. So specifically, what that means for me is instead of taking the expectation, I'm generating the scenario set S for my parameters. For each parameter, I'm working out the value of the function that I want to minimize. And then I'm taking the expectation by just assigning probabilities to each one of these scenarios. So that's stochastic optimization kind of in a nutshell. What you want to do is you want to somehow minimize, subject to some decision space, the expected outcome of a solution, of an approach, where the expected outcome is kind of calculated in terms of these discrete scenarios. So I'm choosing a set of scenarios. I'm assigning a probability to each scenario. That's the PS. So I'm giving some value PS to each scenario. Then I work out what G is, what the outcome of taking a decision Y is with respect to if this scenario happens. And then I'm summing over all of the scenarios. So I'm taking the expectation. So I'm still taking I'm still trying to optimize the expectation of a decision. In this case, the expectation of the outcome of a decision. And in this case, I'm calculating the expectation subject to some discrete probability measure. If you want to be sort of rigorous about it, what it means is we've discretized the distribution of DIC-C. We're just saying, okay, there's only a finite number of outcomes. For each one of those finite number of outcomes, I can work out what the outcome of my decision is. And I take the weighted sum over the scenarios. So this is the stochastic optimization approach. And if you go to kind of optimization conferences or seminars, this is where they usually start. So they just say, well, as we all know, what we usually want to do is we want to generate scenarios and then optimize. And that's an interesting problem. It has the advantage of being quite, well adapted to uncertainty, because there are still probabilities flying around. There's still, it's still very probabilistic. But at the same time, I can actually calculate these things. So rather than calculating some abstract expectation, which in general would require me to calculate some integral over some multidimensional space, which I may or may not be able to do, I can certainly do this, right? This is a finite sum of things, so I can calculate this. And in particular, it means that it's taking the stochastic problem and turns it sort of in a deterministic problem. Because if you think about it, the decisions Y, well, they just sort of, this is just a deterministic function now. So I'm just optimizing over a deterministic function with respect to some decisions. So there's a lot of numerical work on this. So in particular, in the operations research community, what they would now do is to think about different algorithms on how you can solve this. That's kind of the general approach. The problem with all of this, or one of the big challenges, is computational complexity. So in order to properly model this, in order to properly explain the uncertainty in some way, you have to generate lots of scenarios. Think about just, let's say you want to predict the weather next week, okay? And you want to take some decision based on that. Well, there's a lot of different things that could happen in the meantime. And if you want to realistically model what's going on, you will need lots of different scenarios. And that's only, weather next week. But if I want to take a decision like optimizing my warehouse flow in the next year, a lot of different things can happen. And if I want to be realistic about it, which I need to be because this is just a model for reality, well, then I have a problem. I have lots and lots of scenarios. And that means that it takes quite a long time to calculate the solutions. That's one problem. And the other problem is it makes it very difficult to understand what's going on behind the problem. Because one of the questions you might always ask yourself is, okay, now I've understood what the best decision is. Well, the scenarios are just a model. What if my model changes? So it's very difficult if you have lots of scenarios and you're optimizing this numerically. It's very difficult to understand how the uncertainty has actually influenced your decision. It's very difficult to say, well, actually, if you now reweight the probabilities, let's say you introduce new scenarios, or you just change the probabilities on the scenarios, it's very difficult to understand how that influences your decision. If you make, let's say you think that previously you thought, let's say you thought that the probability this summer that the infections will be really low. If I'd asked you mid-November, a lot of people would have said, well, there's probably, COVID will sort of be reduced in impact. And then came Omicron, and within a few weeks, the assessment of probabilities completely changed. So now you might have to just rerun your entire model. And every time you have a new decision, you have to rerun your model. So on the one hand, this assumes that you have infinite computing power, which you may or may not have. Computing power now is cheap, but it's not free. But on the other hand, sometimes you have to take decisions quite quickly, and these things take time. So you have the problem that you need to kind of adapt to this complex problem that you may or may not be able to solve. But even if you are able to solve it, you have to solve it quickly enough to actually get an answer. There's no point in me getting an answer tomorrow what I should wear today. That doesn't help. So I kind of have to do this in a real time. So all of this is just to motivate questions around reducing complexity. So in general, the set of scenarios I have to generate is very, very large. But I don't want that. I want the set of scenarios to be small for different reasons, for computational complexity reasons, for reasons of better understanding the problem, and so on. Okay, so that's the general approach. So the idea is simply that you, for every scenario, you have a prescriptive model. You have a decision that you take. And sort of what we were thinking is, well, what we're really interested in is not the scenario. So I need lots of scenarios to explore my probability space. But maybe different scenarios can lead to the same or similar decision. Maybe very different scenarios in terms of the parameters that they represent can lead to very similar decisions. And that would be very interesting, because that means that there's a sort of different sets of my probability space. If they lead to a similar decision, well, then from the decision maker's point of view, maybe it doesn't matter so much which of these uncertain parameters come out. The outcome could be something that's similar. And in that case, maybe I don't care. Maybe I have this whole set of different outcomes, and maybe we can argue lots about which of them will happen. But if the decision is actually the same or similar, well, then I don't really lose anything by not deciding, or by just saying, well, it doesn't matter so much which of the two happens. Of course, on the other hand, it might be that at some points I have kind of discontinuities where even a small change in the parameter leads to a drastically different optimal solution. So in other words, what I need to understand is the connection between the decision that I'm taking and the parameter that's led to this decision. And I'm just going to pause a second if there's any questions, because I'm not really all that good with the Zoom talk. So if someone has a question, just please go ahead. Okay, so so somehow the approach or the problem to be solved is understanding how different scenarios might be able to lead to a similar decision. Okay, so that's now starting to sound a little bit more like something to do with unsupervised machine learning, because somehow I want to group the scenarios according to the decision. Okay, so this is some sort of clustering problem, and it turns out you can actually formulate this very well in terms of a graph clustering problem in the following way. So let me just say that, be again a little bit more precise about everything. So this is, by the way, this particular project is joint work with Michael Hewitt from the University of Chicago, Loyola University of Chicago, and postdoc Julien Cocher in McGill, and also Walter Ray, who's a colleague of mine here in our department. So to be a little bit more precise about all of this, sorry about that. What I want to define is the outcome of a decision that I'm taking if a particular scenario occurs. So I've called this G of Y and S before. So for any specific scenario, I can solve the optimal problem. I minimize the cost, for example, by working out the optimal decision if I think this scenario absolutely happens. Okay, but now, so in other words, what I'm basically saying is I'm supposing that there is a oracle that tells me actually in reality scenario S will happen. Some scenario will happen. Okay, so now I go back to my optimization model and I say, okay, I minimize the cost according to if this actual precise scenario happens. So if I do that, then I might be wrong. I might be right or I might be wrong. But what I'm interested in is understanding, well, if I'm wrong, let's say that I think that scenario S1 happens, but actually scenario S2 happens. How bad is this? So in other words, what is the difference between the outcome with my solution according to scenario 1, if the scenario 1 happens, or the outcome of my scenario 1 if I solve according to scenario 1, but actually some other scenario happens. This is called, and I can just take the difference of these two. This is going to be a positive quantity because I'm minimizing. So, you know, taking the difference, if I'm wrong versus if I'm right, I'm going to be wrong some bit. But this is going to be something that tells me how bad I'm wrong. So for example, if this distance is very small, what that means is that actually whether scenario 1 happens or scenario 2 happens, in terms of the decision that I'm taking, it doesn't make much of a difference. It's more or less the same thing. On the other hand, if this distance is very big, well, then getting scenario 1, but actually scenario 2 happening is quite costly, is quite bad. So in other words, one way of thinking about all of this is to say, well, this is telling me something about how the scenarios differ, not in terms of the parameters that they represent, but in terms of the outcomes. So if this opportunity cost is small, that means whether scenario 1 or scenario 2 happens, in terms of the optimal solution, it doesn't change much. So these two scenarios should be close to each other. On the other hand, if the distance is big, well, then that means that scenario 1 happening and then getting that wrong for scenario 2 is really bad. So these scenarios should be far apart. Okay, so this is the opportunity cost. This is not a distance yet because it's not symmetric. It's not clear that getting it wrong one way gives you the same opportunity cost than the other way. So what can you do? You just symmetrize it, and so you get something symmetric, and it's a distance. So this gives you a distance on the graph of scenarios. So you're basically thinking about each scenario point as a data point, and you have a distance between any two scenarios according to your this opportunity cost. And the task now becomes identifying groups of scenarios for which the opportunity cost is small. Because if the opportunity cost between a set of scenarios is small, that means that essentially any one of these scenarios gives you more or less the same solution, or gives you a near optimal solution. And if I can find groups of scenarios like that, well, then I can reduce complexity, I can understand better what's going on, and so on. So in other words, what I've motivated here is a graph clustering problem. I'm just trying to find groups of scenarios according to some weighted graph with some distance on it. You can think about it embedding it in some high dimensional space and actually, you know, making lengths according to what the distance is. But that has an outcome in optimization. Namely, it tells me that if I find these groups of scenarios, well, then I can do interesting things in terms of optimization. Again, I'm going to just pause a second in case there's any questions. No questions. Okay. So in terms of what does that mean in terms of clustering? Well, okay, so this is the part that when I talk to sort of optimization audiences, I spend more time on. So I'll be a bit quicker here. So the simple thing is, I think about these scenarios as somehow being points. Okay, in this case, in two-dimensional space. And here's a very nicely clustered example. So in this case, I have some scenarios for each group. So I can, you know, sort of assign colors to these groups. This is my graph clustering algorithm. And then one of the things I could do, for example, is for each one of these groups, I just pick one scenario, maybe one in the middle. Okay, and so now I've started out, let's say, with 100 scenarios. And let's say I found, what's there, like 7, 8 clusters. If I take only one scenario from each cluster, the error of solving this much smaller problem with only 8 scenarios should not be so big, because I've basically replaced each scenario that I've taken away by something for which the solution is very similar. So in other words, I've drastically reduced the complexity of my optimization problem, while at the same time not paying too much of a price in terms of the approximation that I'm taking. So this is very interesting, because in most optimization problems, the complexity grows quite strongly, quite fast in terms of the number of scenarios. So it's usually some fairly high polynomial power, or sometimes it's even exponential. So it's really interesting to be able to go from 100. If I can go from 100 scenarios to 10 in a discrete optimization problem, I'm going to be able to speed up a lot, find much better solutions, and have much more time thinking about the individual discrete optimization problems that I can do. So that's kind of what I can do in this case. And of course, there's a sort of trade-off, right? In general, in this case, I cheated and I said, well, okay, there were sort of clearly predefined clusters. In reality, these clusters are not so nice. So I kind of have to do a trade-off where on the one hand, if I take fewer clusters, my complexity reduces, so I can get better solutions. But at the same time, of course, the approximation gets worse. Whereas on the other hand, if the complexity increases because I have more clusters, well, yeah, then I have to sort of solve a more complicated problem, but at the same time, the decision is going to be more closely related to what's happening before. And the nice thing is I can actually calculate how bad the approximation is because I have my opportunity cost distance. So I just need to look at the diameter of each cluster. And if the diameter is small, then I know my approximation is good. So that's kind of the general idea. I want to sort of find structure in the scenario space in order to, so one of the things that I can do right away is to get nice upper and lower bounds for my original problem. And the nice thing about calculating upper and lower bounds at the same time is that then you can see how bad the approximation is. So, oh yeah, so that's a good question. So I just saw in the chat someone asked, what determines whether the diameter is small or large? Well, it's the diameter in terms of the opportunity cost distance. So in the little example that I showed, the sort of, the X and Y direction, the way you should think about the Euclidean distance here is that I'm sort of embedding the fact that I have a notion of distance between any two scenarios according to this, this opportunity cost distance. So by diameter, I just mean in this cluster, it would be the distance between maybe this point here and this point here. So it's the largest opportunity cost between any two. And so in general, there's different ways of approaching this trade-off between complexity on the one hand and the number of scenarios on the other hand. So what we found works best is to actually look at the quality of the clustering in terms of what's called the silhouette score. So it's basically a way of comparing the diameter of each cluster, the opportunity cost distance between two scenarios in the same cluster, and the opportunity cost distance between different clusters. And if that ratio is very small, then the clustering, I mean, this is a sort of abstract notion of measuring a clustering, but it also means that it will give you a good approximation in terms of the optimization problem. But it's not, I mean, it's a very good question in the sense that it's not necessarily something that you can say in advance, well, the clustering has to be this good and then it works well, because obviously a lot depends on the actual specific optimization problem. So what we found works best is to kind of take this trade-off in such a way as to minimize the silhouette score and then to take this value in particular. I hope that sort of answers the question.
Oui, en français, en anglais? Pardon. So, thank you. I would like to know, how does that approach, how does that compare to a principal component analysis that we would do on the possible scenarios?
Right. Yeah, so that's a very interesting question. So PCA is another way of reducing dimensionality by trying to reduce the variance. But the difference is that in order to do principal component analysis, you have to have components. So in other words, you're thinking about the scenarios as being embedded in some Euclidean space. And this is where my little diagram breaks down. In reality, all I have is this opportunity cost distance between scenarios. So one of the previous approaches, what people have done in the past, is to find different clusterings, for example, PCA or some sort of k-means on the scenarios when I represent the scenarios as their parameters. So let's say that the scenario represents, let's say, the price of oil today and the economic index of today. Let's say I do some economics problem. Well, in that case, I have two dimensions. I have the price of oil and I have the index that I was talking about. So in this case, I'm in some two-dimensional space, and I can do k-means, I can do PCA. But what we're interested in is measuring. So in that case, you're measuring the distance between two scenarios as the Euclidean, let's say, distance or L1 norm or whatever between the 2 points. But here, what we want to do is we want to think about the distance in terms of the outcome, the opportunity cost distance. So the complication is that this is not a Euclidean space. I mean, maybe you can embed it. I mean, I guess you can embed every graph in some super high dimensional space, but that turns out not to be the right thing to do. So it turns out to be better to think about it in terms of a graph. And in that case, PCA it's not the right thing to do. But it's true that what I'm talking about, this kind of graph clustering, is very similar to something like a PCA approach or a k-means approach or something like that.
Thank you.
Okay. So the question was, what do I mean when I say small versus large? And this is where the trade-off comes in. So it depends on the individual problem. So by small, what we do in general in this case is we look at, so I mean, obviously in reality, they will not be so nicely clustered as in this little picture that I'm showing. What I do in reality is I do the clustering into 2 clusters, 3 clusters, 4 clusters, 5 clusters, and so on. For each clustering, I calculate the silhouette score, which is basically the ratio of the diameter of each cluster with the distance between the clusters. So I'm sort of looking at, for each point, how close is it to the furthest point in its own cluster versus the other clusters. And then I pick the K, so the number of clusters that optimizes this score. That's what ends up happening in reality. So it's not really like there's a threshold as such, where we can say, oh, this is small, this is big. It's just we kind of do the best thing we can. And there's no a priori guarantee that this will work very well, other than the diameter gives me kind of an upper bound for how bad my approximation is.
Tout ça est lié à l'apprentissage machine non supervisé. Mais juste pour te donner une idée, Janosh, il y a des étudiants, pas forcément qui ont un background en informatique, qui viennent d'autres domaines, des sciences humaines, et n'ont pas forcément beaucoup de connaissances en machine learning.
Okay.
Et surtout pas en unsupervised.
Donc je voulais expliquer un peu plus comment ça fonctionne exactement à l'intérieur, mais pas trop. Donc, je ne vais pas trop rentrer dans les détails. Donc, yeah. But what I think everyone, okay, so if let's say unsupervised machine learning is something that you have never seen before, or something you don't really know very much about, the key idea is doing this little game that I did here. So the idea in unsupervised machine learning in general is that you're presented with a picture like this. So you have some points, and what you want to do is you want to find groups of points that are close to each other. And by close in general, we would mean, in this case, the Euclidean distance between the points. So just you measure kind of with a ruler how far they are from each other. And then what you want to obviously do is to sort of say, well, here's a group of points that are very close to each other. Here's a group of points that are close to each other. Here's a group. So what I'm saying is I'm taking subgroups such that each 2 points in the subgroup are close to each other, but very far from other points. So in that case, what you should think about as clustering is assigning groups to these points. So in this case, I've done it in colors. So each color represents one cluster. And in this case, it's visually clear that each group has this property that the points are very close to each other, but other points are far away in comparison. So one way to think about it would be like this. And actually, that's exactly what happens. The only difference is that the distance, so the idea of saying what does it mean for 2 points to be close, is more complicated. And in the present case, it's exactly the distance as saying, if I solve for scenario 1, but then scenario 2 happens, do I still get a good solution? Then they're close. Or do I get a poor solution? In that case, they're very far. So that's really what we want to do. Sort of technically, it gets a little bit more complicated because now I have actually this distance is a bit more difficult to think about. The best way to do it is to think about it in terms of a graph. So what you want to think about is that each scenario is 1 point, and you put a kind of rigid line between any 2 scenarios that corresponds to the distance. So in that case, you have some sort of graph of points flying around that are, very sorry, that have the property that if 2 points have a very short connection between each other, they're close to each other. And if 2 points are far away, they have a long point to each other. And so what I now want to do in terms of the graph clustering is to cut some of these long edges so that I have sort of subgroups of points that are very close again, where every connection is very close to each other. And I've cut all the long points so that I have sort of distinct subgroups. And then one of the things I can do in terms of optimization, once I have these scenarios, once I have chosen these subgroups, what I can do is instead of taking this whole cluster with its, let's say, 15 scenarios in it that has high complexity, I'm just going to choose a single one, let's say the one in the middle for each one of these. And now I've gone from having 100 scenarios with all the associated cost to about 10 without sacrificing too much of the optimization part. So technically, this requires some graph clustering, but essentially it just comes down to cutting these edges and figuring out which edges are long and which edges are short. And that's where the machine learning comes into play. There's nice algorithms for this. So there's a nice mathematical computer science literature around this that tells you how you should cut these edges in the right way.
Merci Janosh. Tu as une continuation de questions par toujours Marou. Dans le chat.
Le chat ici. So the definition of the distance is the opportunity cost. So the definition of the distance between two scenarios is to say that distance is how bad my optimal solution is if I think that scenario 1 happens, but actually scenario 2 happens. That's the distance between scenario 1 and scenario 2. I'm not sure if that answers the question. I'm not sure what you mean by step, to be honest. So what do you mean by step? That's the part I'm not quite sure about. Oh, I see. Yeah. So yeah. Okay. So in general, yeah. Okay. So what I'm thinking about is the solution would be some decision that I'm taking. I'm assuming that I can take the decision right away. I'm not assuming that I have to. I'm assuming that if you give me a scenario, I can find the best decision. I can calculate it. It's just that if I have lots of decisions, if I have lots of scenarios, then it gets difficult to find the optimal solution. Yeah, so I guess if I understand your question correctly, yeah, the number of steps could be the. So for each scenario is one of these, I think. I hope. Okay, yeah, that's yeah. So I think that I hope that answered your question. Okay, great, fantastic. Okay, perfect. So I'll pause 2 more seconds if anyone else wants to ask any question right now. Okay, but if you have any more questions along the way, don't hesitate to interrupt right away, and we can discuss right away. We don't have to wait until the end for questions. Okay, so actually, what I was just talking about, there's a formal way of saying this. Essentially, here I have 2 clusters. One is red and one is blue, the other way around. And what I can say is, well, for any point, if my clustering is good, then the distance between any 2 points in the same cluster, so the distance between any 2 red points, that's what I'm calling A here, should be small. And the distance to any point that is blue in the other cluster should be large. So in this case, small versus large means the blue distances should be much bigger than the red distances. And there's a sort of mathematical formula that you can work out. You can sort of basically say, well, I'm looking at the distances between the differences between these distances, and then I'm normalizing a bit. It's just to get something that goes from -1 to 1. And this is called the silhouette score. So it's basically a way of calculating this, of making precise this abstract idea that if my clustering is good, I should have the fact that 2 points in the same cluster are very close to each other, and 2 points in different clusters are relatively far away. If I want to give a mathematical definition of this, this is exactly the silhouette score. It's the ratio of these things. It has the advantage that it always takes values between -1 and 1. And here the idea should be that if you get something negative, that means that your clustering is bad, in the sense that you've wrongly clustered. You've put, let's say, for example, if I put a blue point here, that would mean that my silhouette score gets negative. If the silhouette score is around 0, it basically means that I'm randomly assigning clusters. There's no real structure in the points. And as closer the silhouette score goes to 1, the better the clustering is. So basically what I'm looking for here is to get a clustering such that the silhouette score is as big as possible, because in that case, points in the same cluster are close together, points in different clusters are far away. And in a real problem, not this toy problem that I showed you here, in reality, it's not clear. Here, you look at it once and you can ask any child will tell you that there are 6, 1, 2, 3, 4, 5. Any child will tell you that there are 7 groups of points, right? You can take a 6th grade and say, find groups of points, and they will draw circles around them. In reality, that's not the case. In reality, you have some high dimensional things, so you don't know what the right number of cluster is in advance. And the silhouette score basically tells you, well, choose that number of cluster that makes the silhouette score on average as good as possible, as high as possible. So the advantage of that is that I can calculate this without solving the stochastic optimization problem. It gives me a decision route now. Okay, so I generate my scenarios. Maybe there's too many scenarios. I can't solve my original stochastic optimization problem. Well, now I calculate the optimization, the opportunity cost between any pair of scenarios. That is fairly cheap to do. I do clustering into 2 clusters, 3 clusters, 4 clusters, 5 clusters, 6. For each one, I calculate the silhouette score. And then I choose the number of clusters that has the biggest silhouette score, because that has the best clustering. That's my methodology. So that's what I'm doing. So you know, we're sort of skipping a little bit over the technical parts of how to do the clustering, but in some sense it doesn't matter. Actually, it turns out that as long as the silhouette score is reasonable, we've tried different clustering methods. That doesn't change too much in terms of the outcome. So okay, so what can I do? There's a bunch of maths on this slide, but if you don't want to think about the maths, you can also just think about it in terms of the little picture that I showed you before. What I'm simply going to do is, instead of solving this big bad optimization problem with all the scenarios, so this is the one where I need to find optimizing over lots of scenarios, what I could do instead is choose one scenario for each cluster, right? So this is the picture that I showed you where we had 100 points at first, and we picked one from each cluster, so we went from 100 to 7. And then I can just assign to each one of these representative scenarios the probability of the whole cluster. I'm just saying, instead of thinking that one of these scenarios happens, I just think that this one representative scenario will happen, with the probability being the sum of all of them. So instead of, you know, I'm sort of making this approximation, and then I solve this problem, which has a lot fewer scenarios, and therefore is a lot easier to calculate. And I know it's going to be, this is going to give me an upper bound of the original problem, because I'm actually sort of, the way to think about it is it's sort of like optimizing over the smallest set of solutions. By taking fewer solutions, the infimum becomes smaller, right? Like if you have fewer things to choose from to minimize over, well, then you're going to get something bigger, because you might not find the best solution. So this is an upper bound. You can it's called the MEDOID upper bound, because what I'm doing with the scenarios in this cluster is I'm choosing the one in the middle. That's called the MEDOID, right? In this graphical image, what I want to do is I want to find the point that's kind of as close as possible to all the other points. That's called a MEDOID, and it's in the middle. So I'm taking this cluster of scenarios and just taking one point, and therefore reducing greatly complexity and getting an upper bound. Upper bound means I already know that my solution is going to be no worse than this. The other advantage of this is that this is actually giving me a decision, actually something I can take, that tells me my problem is going to be no better than this. At the same time, I can find other bounds. I can find a lower bound. So this is kind of different mathematical ways of calculating bounds. I don't really want to discuss this in detail. All I want to show you is that there are upper bounds and lower bounds that you can do. I'll actually skip. Oh no, yeah, actually. So how to do this? So I'm kind of running out of time. So maybe I'll briefly illustrate the methodology and then leave it there. So one of the problems that we looked at is a network design problem that you can think of as planning transport. So what you want to think about is that you have a bunch of points, and you want to connect these points. So for any 2 points, you can open a route. You can think of this as building a street between the 2 points, or building a track, or planning some sort of shuttle service between the 2 of them by lorries, something like that. So there's a fixed cost of opening any route, and this takes time. So you have to do this in advance. And then you have a variable cost of transporting certain commodities across these routes. So think about that as actually deciding to put a certain number of boxes onto a lorry. Okay. So in this case, the scenarios, the uncertain parameters, represent the demand for each of these commodities that need to be sent around. Okay. So in that case, it's actually what's called a 2-stage problem. I need to plan the routes before I know the value of the uncertain parameters. And then I need to, and then I get to decide which of the which of the goods I'm sending around after I've taken my decisions and after I've learned the demand. So think of this as planning trucks going around, but on the day you can choose what you're actually loading on the truck today. Maybe today, you know, tomatoes have a higher demand, so I'll put more tomatoes on, but tomorrow I'll put cucumbers instead. So what I want to do is I want to sort of choose a network of connections between these points that I need to do before I know the exact values of the demand of things going around, and then I can transport things around. So in this case, it turns out that our methodology, okay, so this is the optimization problem. We don't really need that. So it turns out that actually, in this case, the clustering that we're doing works really well. So in particular, we're doing much better than just randomly clustering the scenarios. Okay, that's just a sort of sanity check. Of course, you want to do much better than random clustering. But it turns out that actually this really works exactly as we expected. So in terms of numerics, what we did is we generated lots of instances that we tried to solve. So then there are some easy instances where Cplex, which is a commercial solver, also finds the same answers. There are some difficult instances where a commercial solver will not be able to find you the right answer. And there was one instance where the commercial solver couldn't even find you an admissible solution. And what we ended up doing was doing, so these tables are kind of standard in optimization, but I'll sort of skip over them a bit. Basically, what this means is that for the easy instances, we were able to find almost as good a solution as the commercial solver, but in much, much quicker time. So maybe just to point this out, the commercial solver takes 3,000 seconds in mean and 800 seconds in median to solve the problem. And for us, it was around 10 seconds. So we were able to speed up the solution by a factor of, let's say, 100 or more, which is really good because in a lot of problems, that means that you can solve them more quickly. And for the solutions that the commercial solver was not able to solve, we were most of the time able to solve them. So we get smaller gaps. The gap is basically the difference between the upper and the lower bound. So how far away you are from finding the best solution. But again, if you look at the times, the commercial solver takes on average, tens of thousands of seconds. So that's, I'm never very good at this, and it's hours of calculation time. Whereas for us, it still only takes a couple of seconds. So what that means is that by doing this clustering approach, you can actually get very good approximations, almost as good as any other ones, but in a much, much smaller time frame. And therefore, in terms of decision making, that means that you can take decisions much more appropriately to the time frame that you're working at. There's no point in me telling you tomorrow what you should have loaded on the lorry yesterday. So I can tell you today now. And the other thing that I want to maybe just point out in this table is that this n star is the best clustering size. So how many clusters should you actually use? And it turns out that the number is very small. So the median number is 2, which means that for more than half of these 17 instances, actually the best way to cluster the scenario space is just into 2 groups. So you actually get very, very good approximation with very small number of scenarios, representative scenarios. And that's really interesting because if you have a small number of scenarios, that means you can actually analyze what's going on. You can look for each scenario what your best decision is. So you've sort of found a very, you found a sub-problem that you can actually understand much better and therefore solve in a much more sort of intelligent way, and also better understand the decision-making that comes into it. And I'm well over my the time that Fatia said I should take, so I apologize a little bit for that. And I'll end here. Thank you very much for your attention. And if you have more questions, I'd be delighted to answer them or discuss them.
Merci beaucoup. Merci Janosh pour la présentation. Et sinon, Janosh, tu peux donner plus d'exemples si tu as préparé d'autres acétates.
Je peux peut-être parler quelques minutes sur si tu dis qu'il y a des gens sciences humaines, sciences
oui,
sociales.
C'est un programme multidisciplinaire. Exact.
Oui, donc juste, donc l'exemple que je vous ai donné était très recherche opérationnelle. Un autre exemple qui est très intéressant, ok, on va skipper pas mal ici. Ça, c'est un travail plus récent avec 2 experts en logistique humaine. So in humanitarian logistics, there's a very interesting kind of application to all of this. So this is joint work with Emilia Grass, who's a postdoc at Imperial, and Burcu Bajic, who's a great expert in humanitarian logistics. She's from Istanbul in Turkey, and also with Walter Ray. So basically, the question is the following. If you do humanitarian logistics, you need to rely on understanding what the actual situation is on the ground. But the problem is that what you need to do, so what people often do is they go to the different local experts on the ground. They ask, what do you think, let's say, is the population in this city? But the problem is that they don't agree. And not only do they not agree, but they actually contradict each other. So this example that I'm showing you here is the distribution of a certain demand for a certain good in a city in Syria, where one expert, so that's in yellow, says, oh, it should be no more than 10,000. And another expert says, oh, it's more than 15,000. So not only do they not agree, but they actually contradict each other. You can't have both. One of them has to be wrong at least, maybe both. So in this case, but the problem is you don't know who to trust. You have different key sources that all do their best on the ground, but the situation is so chaotic that you don't necessarily know which of the predictions are right. They might just all be wrong. So in that case, what do? You can't just sort of take the aggregation, because, you know, what is the aggregation between these two distributions? Should you just take 15,000 because it's kind of in the middle? It doesn't really make sense. And so this is kind of the problem that we're looking at is in the Syrian civil war, where in this region, IDLIB, which is close to the Turkish border, is very heavily hit by this. So they have this big problem that they want to build shelters for people to hide in, to get services, to get helped, displaced people. But if you don't know how many people there are in a city, or what the demand for a particular good is, it's very difficult, because how many shelters should you build? So the question is, where should you build these shelters? So the data, the uncertain parameters here are the demand for such help in general. So it could be the population in a city, it could be the number of children, the number of vulnerable people, and so on. So in this case, what we do is, again, have a sort of two-stage decision process. You want to open these shelters. You can't open the shelters every day. You can't build new shelters every day. So you have to somehow build the shelters based on this very patchy information, because you have to distribute all the goods to build the shelter. But then once you have the shelters built, you can, on the day, kind of assign people according to the different places. But the problem is that the information that you're getting is contradictory. So you don't know what you should do. So what you could do is, again, sort of generate scenarios by including all of these informants, and then try to solve this. But this is bad, because you don't know whether you're right. So what we were looking at is, can we find consensus decisions even though the predictions are different? So in other words, maybe they disagree on the parameters, but maybe we can find some joint decision based on this clustering that gives you some answer. And it turns out that works quite well. So in this case, what we do is we generate these scenarios from the predictions of each source. We calculate the opportunity cost distance. So again, we try to find decisions that unify we try to unify the scenarios from the decision point of view. And it turns out that you can do that. You end up getting different solutions, but that actually work out better for each one of the different experts. And then we basically weight the scenarios according to, we kind of try to sort of encourage stochasticity. We want to give more weight to experts or key sources that predict different clusters, that basically give you a more kind of a hedging solution, if you want. And that turns out to work quite well. We end up actually assigning a lot more people to shelters in the case study that we looked at. And we can actually get better solutions that work better both for the humanitarian needs assessment and for the REACH study, and therefore getting better solutions that work more on consensus. So that's one of the applications for this, where it actually gives you a sort of real life edge on helping people get better services, get assigned to have better humanitarian logistics solutions.
Merci beaucoup. Je souhaite une très belle fin de journée, fin de matinée à tout le monde, et au plaisir de se revoir dans un autre séminaire DIC. Merci, Janosh.
Merci à vous. Merci. Bonne journée.
Merci.